Hi, in this video we will introduce null space for matrices. After row space, column space, this is the third subspace that we associate to a matrix. Okay, so let us start with the matrix. So let A be a M by N matrix. We already know what is row space for this, what is column space. For the null space, we first to prove something, theorem, which is the set of all solutions for the homogeneous system AX equals to 0. So you consider all x's which satisfy this equation, form a subspace for R. So if you collect all the solutions of a homogeneous system, put them all together, that will give you a subspace. Well, to prove this, what we need to show first, we need to show that 0 is a solution. 0 is a solution. But we know this is true always for all homogeneous spaces. 0 is a solution. So 0 will be in that set. That's the first condition. The second thing is that we need to show that this is closed under the addition. In other words, if a u is equal to 0 and a v is equal to 0, then a u plus a v is going to be equal to 0, the add of two zeros, and that means what? I can apply the matrix multiplication being distributive over the matrix addition. We have this fact. And what we showed is that if u and v are in this set, the set of solution, u plus v is going also in the set of all solutions. And the third thing is that if it is closed under scalar multiplication, in other words, if a u is 0, then if you multiply it by c, you can bring it inside. Well, this is going to be actually c times this, and this means that a times cu is equal to 0. What did we show is that if u is a solution, cu will be a solution. So that means that cu is a solution. This way we have proven all three conditions, and that completes the proof. So the set of all solutions of homogeneous system is a subspace. And now that we know that, we can define definition. The null space of A, the matrix A, which we denote this guy denoted by null of A, is the subspace of all solutions of the homogeneous system AX equal to 0. So if you put all these solutions together, that's a subspace. We call it null space of the matrix. We denote it by NULL bracket A. So null of A. That's the third subspace. We will see more relation between these three subspaces, but here I'd like to finish video with some examples. Oh, sorry. Paste. Okay. So I have two vectors. I want to see if these vectors are in the null space of A. Well, checking if something is in the null space means that we need to check if A, V, or AX is equal to 0 or not. So in this case, so for this guy, negative 3, 2, 1, we multiply 1, 1, 1, 2, 1, 4, 0, negative 1, 2 to the matrix negative 3, 2, 1. And what do we get here? This is negative 3 plus 2 plus 1. Then we get negative 6 plus 2 plus 4. And this is 0 minus 2 plus 2. And as you can see, this is 0, 0, 0. That means, yes, this guy is in null of A. How about the other one? Well, the other one, 1, 1, 1, 2, 1, 4, 0, negative 1, 2, multiplied to 1, 0, 2. What does this give us? So this is 1 plus 0 plus 2, 2 plus 0 plus 8, and this is 0 plus 0 plus 4. As you can see, this guy is 3, this is 10, this is 4. Obviously, this is not 0. So this means that the vector 1, 0, 2 is not a solution for the homogeneous system AX equal to 0. So this is not in null of A. How can we describe or find the description of null A? Well, that is clear. So you're trying to find solutions of 1, 1, 1, 2, 1, 4, 0, negative 1, 2, and then x, y, z equals to 0, 0, 0. You want to solve this guy, yes? So this means that you form the augmented matrix. And solve this guy. Well, okay, so to get rid of this, we do R2 minus 2R1, which gives us a 0, minus 1, 2, and 0. The rest stays the same. Then we will get rid of that one by doing row 3 minus row 2, which will give us 0, 0, 0, 0, 0, negative 1, 2, 0, and 1, 1, 1, 0. This is row echelon form already, but to make it easier, we can also do make that 1, 0. So we get row 1 plus row 2. This way we have 1, 0, 3, 0, 0, negative 1, 2, 0, 0, 0, 0, 0. So these guys have leading 1. So x will be a leading 1, having leading 1, y leading 1. But the third variable z here does not have leading 1. So that means that this is z is going to be our free variable. Then minus y plus 2z is equal to 0, and x plus 3z is equal to 0. So back substitution, x is going to be negative 3t, y is going to be plus 2t, and z is t. In other words, the null of A is equal to all x, y, z such that x is negative 3t, y is 2t, and z is t. And as you can see, this is a line through origin and parallel to the vector negative 3, 2, and 1. That gives you everything that you wanted to know about this one. Okay, so the null space is the set of all solutions of the homogeneous system AX equal to 0. We showed that it is a subspace, and we have this notation for null space.